Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there.
Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing the OCR A-Level Chemistry A paper from June 2018, and this is paper 2. This is the paper that I did when I did my A-Levels as well. So which compound is used as a standard for NMR chemical shift measurements? So the main one is that we're using tetramethylsilane because it's a volatile thing, so it's easy to remove, and it's also inert, which means it's not going to react to anything. So that's got to be A. Now the reason it's not B, C, or D is because all three of these are used in proton NMR spectra to get rid of an OH peak. Which compound is a secondary amide? So you should be able to recognize immediately that an amide has this in it, a CONH, right? And if it's a secondary amide, then this nitrogen, will have another replacement carbon on it, so it'll have two things on it. So immediately we're looking for things that have this in it and two things. That does not have a C double bond ONH in it, so that's out. This one doesn't have a C double bond NH on it, so that's out. Our two options are here: C double bond ON, C double bond ON, right? Now, if it's a secondary, what that means is that two of the hydrogens have been replaced on it. Because remember, this would have been like NH3 at some point. If it's got secondary, two of those H's have been replaced, which you can see is here and here, so it's C. That's a tertiary one because there's 1, 2, 3 different things there. So which of these compounds do not react with nucleophiles? So we need to look for a carbon that's electron deficient. So for example, it'd be bonded to an oxygen or bonded singly to an oxygen. So this is an aldehyde, which will, because you can reduce it with an ABH4, so that's out. And the same goes for this ketone here. Here we have CH3, CH, CH2. So CH3, CH, CH2. It's an alkene. Now, this alkene doesn't have any electron-deficient carbons in it. Actually, has this really, really fatty electron-rich area there. So that's going to be reacted with an electrophile instead of a nucleophile, because a nucleophile is an electron-paired donor. It wants to go for something that is deficient in electrons, so that means it's got to be B. And here, this is a haloalkane or halogenoalkane. So as for D, we can see that it will do because that's a halogenoalkane or haloalkane, where this is delta negative, that's delta positive, because the electrons are more shifted towards this side, which means it would get susceptible to attacking by a nucleophile. So that means 3 is B. So which structure represents an alicyclic compound? So an alicyclic compound is where you've got a ring of some sort where it starts and finishes, in a continued shape, but it can't have benzene in it. That's what alicyclic means. So here, that's benzene. That's a Kekulé model of it, so that's out. This is a benzene, that's out. That's not a benzene, so it might be this one. And that is a benzene, so that's out, so it's got to be C. It says which molecule is not planar. So a planar molecule is one that has like a flat region within it, right? So if I take C2H4, it's going to be 1, 2, 1, 2, 3, 4, right? This is flat. It can't be three-dimensional in this part here, so that's planar, right? But if we look at, like, for example, so that one's out because that's planar. But if you look at, like, C2H6, 1, 2, 1, 2, 3, 1, 2, 3, right? These, each carbon has 4 different bonds. It's going to have a three-dimensional shape. Your sort of, your dashes and your wedges and this and that, right? So because it's got a three-dimensional shape like that, it's got to be B because that's not planar, it's three-dimensional. Whereas here, this is H2 C double bond O. C double bond O again makes this become flat. This part, and then HCN for the triple bond becomes flat as well. And also the way you can tell is that HCN, right? You can treat, so if we have HCN, right? You can treat this as if it's 1 and 2 bonding pairs, 0 lone pairs. So that means it's going to be linear. What is the number of peaks in this HNMR spectrum, right? I think the easiest thing to do is just quickly have a sketch. So that means this could be C double bond O, HO, CH2, CHOH, CH2, C double bond O, OH. Can you see how there's some symmetry here now? That's one carbon environment, and that's going to be the same one here on that side. So there's 1, 1. There's one hydrogen environment. There's the other one. They're both the same because they're both symmetrical on either side. And here there's 2. This one's the same as that, so there's 2, but that's also the same as that, so there's 2 there. There's 3 here, and then there's 4 there, so it's got to be B. Ethanol can be prepared by different reactions. Which one has the lowest atom economy? So a percentage atom economy, remember, is the MR of the desired product over the MR of all products. So we need to figure out which ones we actually care about. So this is what we want. That's got to be the highest atom economy because there's only one product, so immediately we could knock that one out. Here, this is what we want, and that's what we want. So now we have to just quickly work out all the atom economies for these other ones and see what we end up with. So for this one, I get 51%, and then for the next one, which is down here, just as a side note, the MR of the ethanol we want is 46. So that's 36%, and then here, and that one's 43%. So therefore, the answer's got to be C. So the breakdown of ozone is catalyzed by NO radicals, which equation is a propagation step in the mechanism of this process. So what we're looking for is first of all, the breakdown of ozone. A propagation step is where you have a radical reacts with a non-radical to make a radical and a non-radical, right? So in that case, we need to figure that part out. And also we know it's breaking down ozone as well, so we're not going to be making ozone in these steps either. So that's out immediately. NO radicals are formed naturally by lightning and also because of aircraft traveling in the stratosphere, fun fact. So what you end up getting is you get an NO radical plus O3, right? Radical, non-radical makes a radical, NO2 radical plus O2. So radical, non-radical. This radical will come along and attack something else that isn't a radical, so it's going to be the O, and then it'll give you an NO radical plus O2 like this. So whichever one of these fits the bill for this, which is going to be D. So which compound could have produced this IR spectrum below? So what we're looking for is we're looking for each and every peak in this, really. So we've got a nice big long peak from what, to 3,200 to 3,000, like 700-ish, right? So if we have a look at the data sheet, what that would be is an OH and an alcohol, most likely. Fine. So at least we've got that. Then what else we've got? We've got 2,100, 200, 300. So 2,300-ish, what's that going to give us? That could be 2,100, 200 to 2,200 to 300, which could be in our data sheet, the nitrile, right? Now, I've got two main pieces. Let's go have a look. So this one's got an alcohol group, but it won't have the nitrile, so that's out. This one's got CH3, CHO, HCN, right? So if I draw that, 1, 2, 3, CHOHCN, so that does fit the bill. This is a carboxylic acid. It doesn't have that nice little broad peak from 2,500 to 3,300 that you find, so that's out. And then here, that's C double bond O NH. So if you look for the C double bond O, you would expect to peak at about 1,600-ish, which there isn't, so that one's out, so it's got to be B. So benzene reacts in an organic reagent in the presence of a halogen carrier to form phenyl ethanone. Which organic reagent is required? So when you're doing this, you need to use an acyl chloride, right? So we're going to have this, and it would have had a Cl originally here, and then that Cl's been replaced, and then it slaps itself on here. So whichever one of those fits the bill here. So in that case, it's got to be C. So now it says, how many straight chain structural isomers of this contain a chirocarbon, right? So if we do 1, 2, 3, 4, 5, 6. It's not, you can't really branch it or do anything else interesting with it. All you can do is move the Cl around, right? So this, if I put a Cl here, that's going to be this one here, this Cl, that's an H, and then all of this. So that's one chiral carbon. If I then move the Cl here, we've got one of this and this and this, and then the H here, and then all of that. So that's 2, right? But then if I put it here, there's the same thing as this one from before. And then here as well, it's the same from the one before and the same from the one before. So the only option is that we have 2 chiral carbons, which is B. So now it says, here's a mass spectrum of this thing here. Which one gives you the peak with the highest relative intensity? So if you have a look at the highest relative intensity, that gives you an MZ value of about 43, right? So we're looking for something with an MR of 43 that could have realistically broken off of this. So if we look a bit through our options, remember that this is a CH, CH2, CH3, CH3, CH2, and then OH, right? So if you have a look, CH, CH2, OH plus, one thing you do is just a rapid workout and see if it fits the bill. So 12 plus 1 plus 12 plus 2 plus 16 plus 1, it gives you an MR of 44. So that one's out. Next, we've got 12 plus 3 plus 12 plus 2 plus 12 plus 1. That gives you an MR of 42. You're out as well. So for the next one, we have 15 plus 15 plus 12 plus 1, which is 43. So that looks pretty good. And then the last one, 12 plus 3 plus 12 plus 16 is also 43, right? So we're stuck between C and D. And we need to differentiate which one it's going to be. So if we have a look, it'd be CH3CO. Where's that fragment going to come from? Because the CH3 is here and the CO is here. You can't just like break it into 2 chunks and then reform it like that. You can only really snap bits off like that. So that means that one's immediately out. So it's got to be C. So which statement supports the delocalized model for the structure of benzene? So this geezer was originally like, yo, Kekule was like, yeah, this is what it is, but we now believe that it's this. And to be honest, it looks more like it is this. The problem is here is if we have this, these double bonds have been different lengths to single bonds. In an actual benzene, they are all the same length. So that is immediately one on the money. Next, the enthalpy change of hydrogenation is less exothermic. So to hydrogenate one of these, it was minus 120 kilojoules per mole. So in theory, if there were 3 of them, you'd do 3 times that. But the actual one was about, that would have been what, minus 360. But in the actual one, it was like minus 200 and something, which is less exothermic, indicating that this is more stable. So that was actually true as well. And here, bromine reacts with benzene less readily than cyclohexene. That is indeed correct, because you can slap bromine on this and it will do an electrophilic addition reaction, but it won't here. It just won't. So there you go. It's all 3 of them. A. So a solid organic compound can be purified by recrystallization. Which of these statements are true? So the organic compound is more soluble in a hot solvent. That is true, because what you want to do is you want to dissolve it in a hot solvent so that while it's hot, you're like, dissolving as much as you possibly can. But then when it gets cold, it starts to recrystallize, come back out and be insoluble. So that way, the solvent is carrying all, and when it's cold, it's dissolved all the other soluble, stuff that we don't need, if that makes sense. So that's immediately correct. The hot solution is cooled before the purified compound is collected. That's exactly what correct as well, because if it's still hot and it's going to have the purified stuff in it, and then if you try and collect it and stuff, you're going to lose bits of it. So that's correct. And then it says the melting point of purified organic compound is lower than the impure. It's the other way around, so that's only going to be 1 and 2, which is B. Next, it says which of the following could react with the compound below to form a carbon-carbon bond. So our options are, we've got a benzene here, so the one thing we could do is use a halogen carrier catalyst and an acyl chloride, right? Or we could use a haloalkane with a halogen carrier catalyst as well to stick the carbon on here. So that's true. That can be done. Next, we have this C double bond O. If I react it with ethanol and KCN, what we'll end up getting is we'll get a hydroxynitrile, but that will add an extra carbon in, so that's indeed correct. And this is an alcohol, an H2SO4, that wouldn't really extend the carbon-carbon bond. That would just make an ester link, so that would be C double bond O, O, C. Can you see how there's an oxygen there? It's not a direct carbon-carbon, so that one's out. So the only one it can be is 1 and 2, which is B. So this question is about the reaction of organic compounds containing carbon, hydrogen, and oxygen. A chemist investigates two reactions of alcohol A as shown below. So what is the systematic name of that? So you find the longest stem first. 1, 2, 3, 4, right? It's going to be 4 something. So we know it's going to be butane something, right? Now I know it's an alcohol. I want to try and put the smallest number to it. So rather than going 1, 2, 3, I'm going to go 1, 2. So that's butane 2-ol, right? So if that's 1, 2, 3, 4, can you see how we have a methyl sticking off there as well? So then we end up having 3 methyl butane 2-ol. Now it says, what's the structural formula of alcohol A? So all you do is you just write like bit by bit. So we know that's going to be a CH, for example, right? And we know it's going to have a CH3, and there's 2 of them on either side, here and here. Then it's going to be CHOH, there, and then a CH3. Done. Now what they do is they heat alcohol A with an acid catalyst to form a mixture containing 2 alkenes, draw the structure of the 2 alkenes formed here. So what we're doing is we're booting out an H2O, right? So the possibilities are that this carbon will form a double bond here, or it will form a double bond there. So in that case, that's what we're just going to draw. Here, here, and then the other one there, like this. The chemist heats alcohol A with sodium chloride and sulfuric acid, construct a balanced equation. So I know that this is an alcohol, right? So let me just write down what we know immediately first. There's an alcohol, we're reacting with sodium chloride and sulfuric acid. So I need to think what kind of reaction we're going to end up having here. What's going to happen is that Cl is going to swap the OH there. We're going to have some substitution. So what we'll do is we'll write NaCl plus H2SO4, because we know those are definitely going to be added. And what we end up with is we've got a Cl here instead, this and this. All right, but we need to figure out what else has happened. So this OH has now been booted off into something else. What it will have booted out of is that you can't just have OH minus on its own. It must have been booted out as an H2O. The H must have come from this, which means we're left with HSO4 minus, but we also had NaCl here. So it's going to be NaHSO4 minus. Sorry, NaHSO4, sorry. Like that. Let me write that a bit neater. NaHSO4. There you go. So compound B is reflux with excess of acidified potassium dichromate to form a single organic product. Write the equation for this. So here, what I can see we have is we've got a couple groups that are going to be doing stuff. We've got a primary alcohol here, and we've got a secondary alcohol here, and a tertiary one here. So this one's going to oxidize, and this one's going to oxidize as well. So because it's in excess, we're going to fully oxidize it all. We're going to be oxidation maxing. So here it's going to be H3C, CH3. That's still going to stay as an OH. You can't have a double bond O here. There's not enough bonds for it to do it because it's a tertiary alcohol. Here, this is going to turn into a ketone, so it's going to be C double bond O. And here, that's going to become a carboxylic acid because that's an aldehyde bit there. So it's going to be C double bond O, OH, right? You should be able to recognize immediately looking at that, that's an aldehyde, for example. Or if you looked at this, that's a ketone. So then we need to figure out what else has happened in this reaction. Number one, you can see that this carbon here has lost 1, 2 hydrogens, right? But then this one here has lost 1, 2 as well. So we've lost 4 hydrogens, right? And that's come out, we've added water into this. So what you end up getting is you get 2 H2O on this side, right? But then we need to figure out how many oxygens we've added as well. You can treat that as the oxidizing agent. So here we went from COH, right? That's still an O there. But you can see we've magically introduced 2 more. We've magically introduced 1 more oxygen here, sorry. So that's 1 oxygen needed, plus the other 2 from this. So 2. So it's going to be 3 there. So you can balance it like that. It works. The compound below shows some reactions of compound C. In the boxes below, draw the organic products. So here we have a carboxylic acid, right? And they've added excess alcohol and acid. So to me, immediately, it's making an ester. So then you would draw the same thing, just with the ester bit instead. So now rather than this being COOH, it's going to be C double bond O, and then the rest of this thing here, CH3, right? So that's COOCH3, and then H3COOC like that. Now, here, they're reacting this with steam and H3PO4. The only thing that is going to react in this is going to be this alkene here, and it's going to make an alcohol. So what you end up getting is HOOC, COOH, double bonds gone, and now we have an OH here instead. Next, it's polymerization, right? So if it's polymerization, it's asking what the repeat unit of this polymer is. So this chunk is going to end up making, but we can't make it in polyesters because there's no alcohol reacting with it. Right, that's a carboxylic acid. It's a carboxylic acid, so it can't be a polyester. It also can't be a polyamide for the same because it's not carboxylic acid and amine. And the only polymerization that can happen here is addition polymerization. So If it's showing you, if it wants a repeat unit, what you do is you would draw it open up like this with the dotted lines on either side, right? Sometimes questions might say draw like a dimer, a dimer, or a certain number of units. If it's not asking for a repeat unit, then you'd close it off. But because it wants a repeat unit, you leave them open. So it's going to be H, and then HOOC, and then this could be COOH, H like that. There you go. So the general formula of an alpha amino acid is RCHNH2COH, right? And it says the alpha amino acid cysteine has this optical isomerism. Draw 3D diagrams to show these optical isomers of cysteine. So when you have optical isomerism, you have a chiral carbon. So start by drawing the chiral carbon, which has 4 different groups. Now, every amino acid in the universe is a C with an H, an R group, and then an NH2 on one side, COH on the other. So you're just going to draw that. So there you go, there you go, there you go, and there you go. So we need to fill in the bits. So the R group now has become this. So CH2SH. We know there's going to be an H on this somewhere. We know there's going to be an NH2 on this, and then we know there's going to be a COH, HOOC. 4 different groups. Can you see how that's chiral? So then, in order to draw the optical isomers, you just draw a mirror image of this thing. So this, COOH, H, H2N, and then just CH2SH. That works. There you go. So now it says this alpha amino acid, lysine, reacts with an excess of dilute hydrochloric acid to form a salt. Draw the structure of the salt formed in this reaction. So when we're making a salt, we're adding an acid to a base. It's going to make a salt plus water, right? So something here has to be acting as a base if we're adding an acid. We need to figure out what parts of this is going to be acting as our base. Now they've told us that the R group now is this. This NH2 can act as a base and accept a proton, like so, to form NH3+. Here, this also has an NH2 in it. So if I just draw this new amino acid we have going on here, so every amino acid, remember, C double bond O, OH, it's got an H, and then it's going to have its R group down here, or you can put it up there if you want, which can be CH2 4 NH2, right? And then it's going to have our H2N here. Because we're adding an acid to it, in order for an acid-base reaction to happen, something else has to be accepting the proton from it, because everything in the universe puts out an H plus as an acid. Anything that takes an H plus is a base, right? So we need to figure out what part of this is going to be taking the H plus. That can act as an acid and lose the H plus, but here it is. What ends up being is H3N plus here, but then this one also can as well, like this, right? But it's asking you to draw the salt. The salt, well, it's going to be whatever this thing is, and chloride. Yeah, so like in the same sense, if you add NaOH, you make NaCl, right? All we're doing is we're just going to make this, but with a Cl minus on it. So Cl minus, and then Cl minus like that. Alpha amino acids can react to form proteins. A short section is shown below. So immediately you should be able to recognize that there are amide links here, CONH like that, right? And you can see them right here. Cool. So then it says a student hydrolyzes this protein with hot NaOH, draw the structure of the organic products formed from this. So when you're hydrolyzing this, what you're doing is you're going to break it down into its constituent monomers again, right? So the monomers that made this up, that must have come from a carboxylic acid, because it does, and this must have come from an amine to make an amine, right? So what we need to do is draw the monomers, but because we're using NaOH, what happens is this carboxylic acid bit actually forms a carboxylate salt, as in it becomes COO minus Na plus. Because it's a carboxylic acid, this is a base, acid-base reaction, make a carboxylate salt. So it's going to be these monomers, basically, just instead of COOH, it's just going to be CO minus Na plus, right? So here, we can see that there's like one end of it, and then there's the other end. Like you see how it repeats again and again. And these are amino acids, so they're going to have a carbon, a hydrogen, an R group, an amine bit, and a carboxylic acid bit there. So the monomer that will have come back out of this is going to be CH, that's going to be the R group, which is CH2, HO, that's the same, right? But then this is going to become C double bond O, O minus Na plus, because we're using base to hydrolyze this, and then it's going to be NH2. That's going to go back to its normal state there, and that's how you get that. So that's one part of it, but then we need to do the other parts. If I just make some more space. So we've got here and here, right? But then this thing is a different amino acid in its entirety. Can you see how there's just a gigantic piece? But don't get thrown off by that, because again, it's the same thing. What we have is we've got our central carbon, we've got an H on it, carboxylic acid group that has become a polymer, and an amine group here, and then this is their R group. So then the other piece that came out of this will have been NH2 here, the CH, C double bond O, O minus Na plus this time though, and then this is the entirety of its R group. So it's going to be what? CH2, CH2, C double bond O, H2N. We're not done just yet though, because we have to break the other amide links here. So can you see how there's a C double bond O and then something else, and then a C double bond O and H here? So there's a amide link here, but then also can you see how there's C double bond O and H2 here as well? So we've got another amide link in both of those areas. So we need to break them back down into their constituent carboxylic acid and amine bits. So it's going to be CH, H2N for this part, but that's going to be C double bond O, and then O minus Na plus, because remember that was a carboxylic acid, but we're using a base to hydrolyze it. Then moving down, we're going to have CH2, CH2, and then this is going to break down back into its carboxylic acid again. So it's going to be C double bond O, O minus, Na plus, like that. That NH2 is like from a different part. So this question's about aromatic compounds. Phenol undergoes nitration more readily than benzene. A student carries out nitration of phenol with dilute nitric acid and forms 2-phenol, nitrophenol, and 4-nitrophenol. A small amount of 3-nitrophenol was also produced. The student thought that carbon-13 NMR spectroscopy could distinguish between these 3 nitrophenols. Explain whether they are correct. So the first thing I'm going to do is have a look at the peaks that you would expect to find here. So you'd have 1 carbon environment here, then you'd have 2 here, right? And then you would have 3 here, and then you would have 4 here, and 5, and then 6. So they're entirely different carbon environments. So 6 carbon environments here, right? If you have a look at this next one, so we've got 1 here, 2, that's different. So 1, 2, 3, because that's different. 4, 5, 6. There's no symmetry here. So these both have 6. Whereas here, this carbon's 1 environment, that's 2, but this is the same as the other one. So those are both 2. Then we have 3, 3, and then 4. So this one at least has 4 carbon environments. So they're partially kind of right. And that's what you would say, is that they can, the 2 and the 3 nitrophenol have 6 carbon environments and would produce 6 peaks, whereas the 4 nitrophenol would produce 4 peaks because it has 4 carbon environments. So you can only tell this, they can only tell apart 4 nitrophenol from the others, but cannot distinguish 2 and 3 nitrophenol. There you go. So then it says, explain why phenol is nitrated more readily than benzene. So what we need to do is we need to have a comparison of what's happening. So phenol, remember, is this here. It's got an OH, and this is your benzene on its own. Now, if we want to nitrate this, what we want to do is we want to put an NO2 on this like that. This NO2 is missing electrons. It wants electrons, and that's an electrophile, right? Where it's getting the electrons from, because it's an electrophile, attractophilia means attracted to, audiophile, for example, somebody who likes audio. If it's an electrophile, it's attracted to electrons. The electrons are coming from this ring. So for some reason, having an OH here means this is better at reacting with this versus normally. The reason is because this oxygen, remember, has a lone pair, but it's partially delocalized into the ring. What that does is it makes the electron density, the amount in a given volume, higher here than in benzene, which means it makes it more, makes it more appealing to that electrophile more, as in it attracts it more, and it's able to react with it and accept, it more and give electrons to this more. That's why. So we're going to say exactly that. In phenol, because you can compare them side by side and figure it out like that. So phenols has oxygen with a lone pair of electrons. These are partially delocalized. They're literally dragged into that ring, into the pi system or ring, right? What this does is this will increase the electron density in the ring, and this increases the attraction of the NO2 electrophile more, and there you go. That's how it works. So methylbenzene reacts with sulfur trioxide to form D as shown below. The electrophile in this reaction is SO3. Complete the mechanism for the formation of D in the curly arrows and show the intermediate as well. So what we've got to do is we've got to think about how it's linked on. We can see that this has joined with an S. So this S has clearly bonded with this benzene ring around here. Now it's told you that it's acting as an electrophile, meaning it's going to take electrons. So when you're drawing a mechanism, you need to make sure that you remember it's all about movement of electron pairs. So as in a curly arrow means an electron's moving from where to where. Whenever you do that, you need to think of it as this bond is now broken, this bond's been made, right? And that's all to do with moving electrons. So you can't just say a bond broke, bond made. You need to say bond broke, electrons went here, bond made, electrons went here. So here, immediately in this diagram, I can see that we've stuck the SO here, so a bond has been made here. The only way we can make that bond is by having electrons from this go to the electrophile there, right? Now the issue here is that this sulfur now has 1, 2, 3, 4, 5, 6, 7 too many bonds, so we need to boot something else off, otherwise it don't work. And as well as that, you can see that this is a single bond O minus. So that means what we have is we have this first thing here, right? And then this bond has to have broken and given its electrons to that oxygen, because then now you have a single bond and you've got that O minus there, right? So then in our intermediate, we're going to have this with a CH3 chilling here. We're going to have our S bonded on now with a double bond O, and a single bond O minus now. But this benzene ring is now giving a pair of electrons away, and it's not got enough. So we need to kick something else off, right? The only route is we kick the hydrogen off. Now, when you, again, break in bonds, you need to say where the electrons go by drawing the arrows. If I draw it this way, That's going to make this a 2 plus, and that's going to make that an H minus, which we don't want. We want to fix this part. So what we do is we move the electrons like this here. And that's how you get that H plus there as well. And that's how you get that ring rebuilt. There you go. So comparing it side by side helps a lot because they love giving mechanisms that are unfamiliar. So this question is about the hydrolysis of haloalkanes. The rate of hydrolysis of a haloalkane depends on the halogen present. State and explain how the halogen in the haloalkane affects the rate of hydrolysis. So when we're hydrolyzing it, what we're doing is we're breaking the CCl-CFCBr bond. Now here, it is nothing, they don't really want you to talk about electronegativity. It's a common thing that people talk about. They're asking you why the halogen in the halogen alkane affects the rate of hydrolysis. So again, hydrolysis is breaking that CX bond. Something is making it either faster or slower. The idea is that the rate is dependent on how strong it is. Because if it's strong, you're going to have to take more energy to actually break it and put it in and put energy in to do the job. So that's what it's going to be, is that, the rate of hydrolysis either slows or, increases the way around if the carbon halogen bond enthalpy is higher, right? Because this would be a stronger bond. We're not done. We need to talk about the actual comparison between all of them. So the CF bond is the strongest and therefore is hydrolyzed the slowest. That's what they're trying to get across, is why is it slow? Not that you can't just yap about electronegativity and this and that, right? So the CF bond is hydrolyzed the slowest and CI is hydrolyzed the quickest because it's the weakest. There you go. So chlorocyclohexane is hydrolyzed with aqueous sodium hydroxide. Outline the mechanism for this reaction and then show curly arrows, relevant dipoles, and the products. So what we're doing is this sodium hydroxide, the actual bit that's reacting is going to be the OH minus, right? The product you're going to make is that it's going to swap with the OH minus. So again, with mechanisms, draw why things are happening. So this bond clearly is broken because the previous question has alluded to it. If a bond breaks, electrons have to go from somewhere to somewhere else, but we need something to actually trigger that. Here, there's a carbon that's delta positive and this is delta negative because of the fact this is not electronegative. And this is a nucleophile because it's got a lone pair that's ready to give it away. So then what it will do is it'll go to that electron deficient carbon like this and form a bond with it. That's what this arrow means. But the problem now is carbon has 1, 2, 3, 4 bonds with the hydrogen here, so 5 really, right? And it's not happy, so it needs to boot something off. So this bond breaks. And the way I like to think of it is, imagine this is your covalent bond, right? And this is electronegative, more electronegative, so the electrons are closer to this. Putting this here, almost in my head, and maybe this is not technically correct, pushes them even closer this way because the repulsion from here, right? So then what happens is bond breaks this way to give those electrons to that. What you end up with is you've now got this with an OH and a Cl minus left. There you go. So a student hydrolyzes a haloalkane using this method. So they put haloalkane E and they reflux with excess ethanol to form a reaction mixture containing F. The reaction mixture is then neutralized with dilute nitric acid and excess is added to the reaction mixture in this precipitate forms. Organic product F has a molar mass of this and a chiral carbon. And then it says draw a label diagram to show how they would do the hydrolysis of this. So we're drawing our reflux up. So what we need to do is we've got our round bottom flask here, or you could draw like a pear-shaped flask. You can't use a conical flask for anything. It has to be one of those ones. And then we're going to have it attached to a condenser. And then the top is just going to be open like this because we don't want it to explode because that's dangerous. Then what we do is we draw a condenser like this and we draw our water in at the bottom and water out at the top so it doesn't accumulate. The whole point is that we're keeping cold water moving throughout the whole system, right? Then what we have is we need to draw the arrow for heat and we need to label this. This is a round bottom flask. And there you go. So now it says analyze the information to identify E, F, and G. So let's have just a quick look at what they've done again because there's a lot of words there, right? So what they did is they got haloalkane E and they added NaOH and you get F, right? Then what they did is they added the nitric acid, presumably to get rid of that. And then they added, so when we've made our F, they then added AgNO3 and you get a precipitate G, right? So they've told us that the organic product F has an MR of 74.0 G per mole and it has a chiral carbon. What else do we know about this? E, we had 0.0100 moles of this and excess of this, and then we have 1.88 grams of G. Anything else we can get from this? That's about it. So what we need to do is we need to figure out what we're dealing with and how we're getting there. So if we think about it logically, we had 0.01 moles of this. These react in a 1-to-1 ratio, so we'd also have 0.01 moles of this. And therefore, these again react in a 1-to-1 ratio with all of these things as well, so we'd still have 0.01 moles of that. So the moles of G is going to be 0.0100 moles, right? Now, we can work out the MR of whatever G is by doing its mass over moles. Because at no point there was no doubles or anything like that in that case. If it was like a halo alkane, then we might have to double things. But here we just know it's one singular halogen group. So if we're going to do the mass over the moles, it's going to be 1.88 grams divided by its moles, which is 0.01. And if we do that, we get 188 grams per mole. So that's its MR. Now we know that this is going to be silver plus something because we're adding AgNO3 and we're getting a precipitate. So it's going to be a silver halide. So then I can work out what the halogen is, or the halide really. So if I do 188, yep, minus the MR of silver, which in this case would be 107.9, we end up getting 80.1. Now if I look at my periodic table, that is Br minus. So we know now that therefore G is AgBr, right? Cool. Now, if we have a look, we know that this original haloalkane must have a Br in it now. That's what we definitely know. Okay? Because when it reacts with this, we get an OH swapping with it, and this and that, blah, 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 and we get an ABr and this and this. So there's that. Now, we know that if we're going to react a haloalkane with an NaOH, we're going to make an alcohol, because the Br will swap with the OH, right? So then at least with F, what we can gather is that it's an alcohol, it's chiral, and we know it is got an MR of 74.0. So I know that F is an alcohol, it's got this MR here. So if I do the MR minus the alcohol bit, because that's going to be an O and an H, right? Then the rest will be carbon and hydrogen. So that means I'm going to take away 16 minus 1 from that. If I do that, we get 57. This 57 is C's and H's. So we need to figure out how many C's and H's we can divvy up into that. So if you muck about a bit with it, you can do a CH3, a CH2, another CH, and then a CH3, and that's where my OH would go. So what we end up is with this. So that's that, right? So now I know what F is. E is just going to be the same thing, but the halogen instead. So the exact same carbon chain. So CH3, CHH with the Br in this, like that, instead of the OH, and there you go. That's all done. Question done. Okay, so cinnamaldehyde and methyl cinnamaldehyde are naturally occurring organic compounds. Methyl cinnamaldehyde is an E stereoisomer. Explain this statement in terms of the Carnot-Gold pre-log CYP rules. So what that means is where these guys came along and came up with the rules saying that the highest priority things are the things with the highest proton number, or the things that are the most exciting groups, really, right? And if they're on opposite or the same sides, then it will affect whether you've got an E or a Z isomer. So here he's told you that it's an E stereoisomer. We need to look for where the double bonds are in this case, which is here. You can see that this part is like more exciting than the singular H there, and here that's way more exciting than the singular H there. So you would say, first of all, why it's an E stereoisomer, which in this case is that the higher priority, I should say, priority groups are on opposite sides. And we need to say what those actually are. So the priority groups that are the highest here and here are, these groups are CHO, and then this whole benzene here, which is C6H5. A student plans to carry out a chemical test on cinnamaldehyde and some methyl cinnamaldehyde. Suggest a suitable chemical test that can confirm that both compounds have an unsaturated carbon chain. Your answer should include the reagent and the conditions. So immediately I'm looking at the C11C and we're testing for that. So you add Br2 and it goes colorless from red-brown. There you go. Then it says, describe a chemical test to confirm that both of them contain an aldehyde functional group. So we're not just going to add like 2,4-DNP or anything like that, because that can give you ketones as well. We're looking for just aldehyde on its own. So if we're looking for whatever's just aldehyde on its own, we're going to be adding Tollen's reagent. The reason is because Tollen's reagent, this has silver in it, which gets reduced. And if you're going to reduce something, you have to oxidize something else. So the aldehyde can get oxidized into a carboxylic acid, whereas you can't oxidize a ketone any further. It's done. So Tollen's reagent, what happens is it gets reduced. So then you end up with a silver mirror forming. That's just solid silver. That's what it's getting at. Now it says, describe a chemical test to confirm that these cinnamaldehyde and methyl cinnamaldehyde contain a carbonyl group. How could these products of this test be used to distinguish between the two compounds? Your answer should not include spectroscopy. So here, this is different. Now we're looking for a carbonyl group, which is where you've got a C double bond O. It doesn't matter whether it's a ketone or an aldehyde, right? So what it's asking is, how can you test for these two? And then what can you do to distinguish between the two of them that isn't what we just said above? So what we're going to do is we're going to add, the only way to do this really is to add 2,4-DNP, right? And what you'll end up making is you'll get an orange precipitate. But that's not enough, because we need to then, it says, how could the products of this test be used to distinguish between the two of them? So how can the orange precipitates be, and analyzed to see what the differences between the two are. So what you do is you take the precipitate and you work out its melting point, right? And then what you do is you compare these melting points to known values, like so. You've got to really be careful to read the question here because it's saying carbonyl group and then what you can do to take the product of this test. If I want to test for carbonyl, that includes ketones and aldehydes, whereas the question before was only talking about aldehydes. So you can't use, like 2,4-DNP would give you it'd give you a precipitate for both aldehydes and ketones, but here they only want aldehyde, and the only one that would do that is toluenes. Whereas here they want to confirm whether, first of all, there's a presence of a carbonyl group, which is ketone or aldehyde, and then how you can take the products of this, which is that orange precipitate, and then identify what it is. So that's how you do that. Now it says the flow chart below shows some reactions starting with cinnamaldehyde. Draw the structures of the missing organic compounds in the boxes, then add the missing reagents on this dotted line. So just pick one and start step by step and compare them. So for example, here I have an aldehyde. I'm adding NABH4. What that's going to do is it's going to reduce it back down to an alcohol, and this is a primary alcohol. So it's going to be the exact same thing here, right? But now what's different is you instead have this C here with an OH on it. That's where that extra bend comes in, like that. Next, we've got this here, and we're adding H+, right? Now with H pluses, so now we've got to this point, we have an alcohol here, and we've got a nitrile, right? So we're adding H+. When you're adding H+ to a nitrile, what you're doing is it's going to get converted to a carboxylic acid as part of that big flow chart. So then what we end up having is you've got the same thing here, but now that nitrile has become a carboxylic acid. So that's the same, but now this has become COOH, like that. So then here we're going from this CHO to an OH and a CN. Nitrile, hydroxy, hydroxynitrile. So what we're going to add is whatever gets us from an aldehyde to a hydroxynitrile, which would be NaCN with acid H+. So those are the reagents and conditions. Now what we're doing is we're going from this, which has an OH and a CN in it, and we're adding excess H2 and Ni. So it's going to be adding the H2 to something, right? So we need to look what's in it. We've got an alkene group, the OH it's not going to react with, and the CN. So this CN will have extra H's added to it to become NH2. It becomes an amine, and this double bond will disappear. These double bonds don't go because that's benzene. It wouldn't do that. So what happens is you get a reduction of that nitrile, and you get an amine, and you also get hydrogenation of the CC. So then if I draw this again now, we have this, this, and this, right? Now this has become a single bond because we've added, the excess gives away that we're doing all of those. So then we end up with this, OH, and then CH2 from there, NH2 there. The fact it says excess is how you know that these and these are going to react because there's lots of it there. Now it says methyl cinnamaldehyde reacts with iodine monochloride via electrophilic addition. The reaction produces a mixture containing two different organic compounds. The electronegativity values of chlorine and iodine are given in this table below. Here we go, and we can see that, unsurprisingly, Cl is more electronegative. Now what it says is to outline the mechanism using the curly arrow model for the formation of one of these organic compounds, and then explain which of the two is more likely to be formed. Then it says, in your mechanism, you can show the phenyl group as C6H5. So here, we need to go look at what's happening in terms of this reaction. So we are adding ICl, right? Okay? So in ICl, what's happening is these are halogens being added to an alkene. So it's going to do electrophilic addition where you end up with a halogenoalkane. Now, the electronegativity bit is relevant here because what happens is we need to generate an electrophile using these two, and we need to add it onto here, right? Now, there's a bit more to this as well. We need to figure out which of these two is going to be the major product, right? This is more electronegative, which means it's more hungry for electrons. If it's more hungry for electrons, then the carbon it's going to go for here is the more stable carbocation eventually, which is going to be this one because it's got this CHO on it and it's got a methyl group on it too. So your chlorine is going to go here, your I is going to go there. And that makes sense logically speaking, which I'll describe in the mechanism as we draw below. So first of all, in this mechanism, what we're going to draw is we're going to draw the entirety of that thing, but I'm just going to change this into C6H5 to make my life easier. So it's very easy to draw it as like a nice double bondy bit and then everything else out there like that. Okay? So if I just draw this, we get this thing here. So C6H5. Now in electrophilic addition, what's happening is an electrophile, electron attracted to, phile attracted to, is going to go to this very lovely, rich, electron-rich double bond there. So the reason that they've given you the electronegativities here is because that's relevant for this first step. Because if we draw ICl, right, this Cl is more electronegative. Each line of these is a covalent bond, remember? So if this is more electronegative, it's pulling the electrons towards itself. So you already have a dipole here. That's delta negative, that's delta plus. And also, by being near these electrons, this dipole is made even more extreme because those electrons are so dense, it's almost shoving these even further, right? So what happens is now that this is electron deficient, it wants electrons from here. So you don't draw an arrow going this way because that says it's giving electrons to here. What's happening is the electrons are being taken from this and given to the eye here. Now, the problem with this is that this eye has too many bonds. It's got 1 and 2 now, and it's like, I don't know what to do. And also, these electrons are very close to here. So what ends up happening is this bond breaks and the electrons move there like that. When you're talking about bond breaking in mechanisms, you need to say where the electrons are going from and to, which is why this arrow stuff matters. The way I like to think of it is that this is electronegative. This has just had an extra whole dose of electrons. This has been shoved even closer to there, so it's eventually giving that final push, breaking it off. Although not technically correct, it just helps me make sense of it. Now, what we could do is we draw our intermediate. So in our intermediate, we now have a single bond here, a single bond here, an H, and then the C6H5 here. And this has now got an I on it because we've just drawn the bond there, here, right? This will have its CHO on it, this will have its CH3, but we've just given electrons away from this double bond to here, so it's actually missing some, so it's got a carbocation there. This has taken the 2 electrons, so you end up getting Cl minus, right? This Cl minus then gives its electron pair to this carbon, so technically speaking, it's acting as a nucleophile here, right? As well as the fact it's electrophilic addition. So then after that happens, what you end up with is you've got the C6H5, we've got the CC, we've got our H, we've got our CHO, we've got our CH3, we've got our I, and then we've got our Cl there. So we've done the first bit where we've outlined the mechanism to form the one organic product. Now we need to explain which of these is most likely to be formed. The reason that this is the most likely is because, so this is your major product, right? You're going to have to say what the minor one is. The minor one is this, but the other way around. So it's going to be the C6H5, CH, CHO, CH3, Cl, and I. Now, the reason it's this is because this Cl wants to go for the thing that has the most stable carbocation, which is here, right? That's the only thing that you guys know content-wise about, major minor product in this mechanism. So you would say is that this Cl is attached to the carbon with the most C atoms. Why? Because it's a more stable carbocation. Because if you think about it logically, this is a carbocation. It wants to take electrons from something. If it's more stable, it's like, come to me, I'm better, I can take your electrons better. And there you go. That's what it is. So this question's about aromatic carboxylic acids and their derivatives. The flowchart shows some of the reactions of compound H. So here's compound H. We have a phenol with a carboxylic acid stuck on it. Now we need to think about what's going to happen. So step by step, we're adding Na2CO3, right? That is a weak base. So what this is going to do is this is going to react with it, but this phenol is not really going to do anything because phenol doesn't react with a weak base. So here we have that. This phenol is the same, right? But this carboxylic acid will have reacted. So what we'll do is it will become O minus because it's lost the H plus because it's acting as an acid and this is acting as a base, and you will then get Na plus here. Now if we add NaOH, that's a strong base, which means it can react with the acid that's a weak acid here, but it can also react with the phenol because phenol can react and act as a weak acid, but it only reacts with strong bases. So here what you end up getting is O minus Na plus here, and then here you'll end up with C double bond O, O minus Na plus like that. Now here we're adding Br2, but this is phenol, remember? So what happens is if you're adding this, you will add on Br2. So you can have up to, 2 or 3 being added, right? There's no question indication saying how much or if it's an excess or this or that, right? So here, it's going to be, so if I just draw the rest of this, it's going to be either here or here mainly or any of these other spots. So I'm just going to put 1. You can do that. Now it says compound H is used in the synthesis of polymer I as shown in this flow chart below. Complete the flow chart by drawing the structure of the acyl chloride and 2 repeat units of I and the formula of the reagents that are required for the first stage of this. So if we just have a quick look. So here we are starting with compound H and we're making an acyl chloride from it. So we need to do something to it. Now the only thing that's going to, so when you're making an acyl chloride, it's a carboxylic acid derivative, which means it's going to be the carboxylic acidy bit that's going to make it become 1, right? Now an acyl chloride is C double bond O with a Cl. The only thing that's going to do this reaction is SOCl2. So what you end up with is you've got the same thing here now, but now you have a C double bond O Cl like that. Work with what the question's saying, right? Then it says we've got this polymer I here, right? And it says 2 repeat units. Now, acyl chlorides can form polymers because they're similar in their behaviors to carboxylic acids. Now, here I can see there's an HO or an OH and there's a C double bond O. So we're going to end up making an ester link like this. So that means we're going to have a polymer in which we have that. Now it says 2 repeat units. When it says repeat units, that's when you leave it open. If it were to just say
two of them stuck together but not repeat, then you would have OH here, but this is a repeat unit, so it's open like that, right? So this end is going to be O whatever. This is going to be linked to a C double bond O, and then the rest of it back to this side. Can you see that? C double bond O is from here to here. The Cl's been booted off in that. And then we get the O, and then the rest of this whole thing again. So O stuck to a benzene like this with a C double bond O, and then a dotted line on the other end for the two repeated units because they're open. There you go. A cosmetic product containing four esters J, K, L, and M are analyzed by gas chromatography and mass spectroscopy, and here are their results. So we've got a gas chromatogram, we've got 4.2, 4.3, 5.9, and 1.0. So now appreciate that with gas chromatography, it tells us the retention times, right? And as well as that, you've also got these numbers here. That's telling you the relative size of the peaks, which is telling you the proportion of each component, right? So that's, there's 4.2 times as many of one of this and so forth. It's telling you how each one is like split. Oh, and also, it says the numbers by the peaks are the relative molar proportions. Fine, whoops. Then it says mass spectrometry, ester J, K, L, and M, and we've got our MZs here. The concentration of ester K in this is about this. Using the results, calculate the concentration in moles per decimeter cubed of M in this cosmetic product, and then give your answer to two significant figures. So first of all, if we look at this concentration of K, they've given it as this in grams per decimeter cubed. We need it in moles per decimeter cubed. So to go from grams to moles, right, we're going to have to divide it by its MR because we want to go, from its mass to moles, right? So moles equals mass of MR. So the concentration of K is actually going to be 9.13 times 10 to the minus 2 divided by its MR, which is 166. And that will give you 5.5 times 10 to the minus 4 moles per decimeter cubed. So now we have the concentration of K, right? Now, in this sense, all of these are in the same volume. So the only thing that's changing, because remember that C equals N over V, the same volume, if the concentrations are changing, it's because of the moles are changing. And if we're looking for M, then something about M is changing, right? It's going to be its moles is changing. So what we've got to do is we've got to look at everything else here and see what's up. If you look here, that concentration is for however many moles of K there is. If we look at K, we can see that it has a relative proportion of 4.3. We want to find M, which is 5.9. So all you've got to do is you've got to make it like, if we think of it as in this is 4.3 shares, this is now 4.9 shares, we need to find out how much one share is. So you would do 5.5 divided by 10 to the minus 4, because if you think about it, this 5.5 times 10 to the minus 4 gives a relative area of 4.3, right? If I were to do 2 times this, it'd be 2 times that. So if I want to find out how much it's giving for 5.9 for the area, to get from here to here, what you've done is you've divided by 4.3, but you've times by 5.9 as well, right? So from here to here, we're going to do the same thing. You divide by 4.3 and you times by 5.9. So then the concentration of M is going to be 5.5 times 10 to the minus 4 times the 5.9 divided by 4.3. If we do that, we get 7.55 times 10 to the minus 4, or 546 really. But we should stick to the same number of significant figures they gave in the question, which is 2. So I'm going to go with 7.5 times 10 to the minus 4. There you go. A general structure for esters J, L, and M are shown below, where R is an alkyl group. Use the mass spectroscopy results to deduce potential structures for J, L, and M. So if we have a look with J, L, and M, what's differing between each of these? So what we can do is we can quickly just work out the MR of this thing and then just use the numbers for everything else, right? So here, that's going to be what? 17 plus 1, 2, 3, 4, 5, 6 carbons plus 1, 2, 3, 4 hydrogens plus another carbon plus 12 plus a 16 for oxygen plus a 16 for that, right? And then the rest is R. So the MR of this thing has got to be 137, right? So then all we've got to do is we've just got to look at the J, L, and M, and then look at what's different. So if I do 137 minus 152, 152 minus 137, what we end up with is 15. Now 15 is most likely going to be a CH3. So then in that case, the R group is going to be CH3. So all it is you've just drawn the entire thing again, same as this, HO, C double bond O, O, and then CH3. So that's that one done. Now if we look at L is going to be 180 minus 137, which is 43, right? Now, if that's the case, then, and they've also told you R is an alkyl group, it's only made of CH2s and CH3s. So that means if I do 43 minus the end CH3, which is 15, that'll tell me how many CH2s I have in between. So 43 minus 15 gives us 28. 28, each CH2 is 14. So that means I've got 2 times CH2 and I've got 1 times CH3. So in this case, it's going to be the exact same thing again. Here, HO, C double bond O, O, and then it's going to be 2 CH2s, so CH2, CH2, and then a CH3 like that. There you go. Now for M, it's 180 as well, right? But it can't be the same as this. So what might have happened instead is we've got to divvy up these CH2s and CH3s differently. So the first thing I'm going to try is see if I can branch off, maybe have like a CH and then put a 2 CH3s off it instead. So in that case, we'll have HO with the same bit here, right? And C double bond O, O. And then rather than having a CH2, CH2, CH3, what I might do is a CH, CH3, H3C like this, because they have the same MR, it just must be differently arranged. And there you go. The relative molecular masses and boiling points of some fuels are shown in this table. Write an equation for the incomplete combustion of heptane. So when you're burning heptane, when you're doing incomplete combustion, write down what you definitely know you're making. You are going to definitely make carbon monoxide and H2O, and you're burning heptane, which has a formula C7H16. Then you start balancing. Always put what you know first, then balance the rest. 7 carbons, so there's got to be 7 carbons here. 16 hydrogens. This is the only thing on this side that has a hydrogen. So that's going to be 8 H2Os there. So then what we need is we need 7 oxygens here and we need 8 oxygens here. So the amount of oxygens we're going to add, because we can only do O2, is going to be 15 over 2 or 7.5. There you go. Now it says explain the difference in the boiling points of the fuels in this table. So if we have a look, hexane has got a boiling point of 69. Pentan 1-ol is the highest. Heptane is the second highest. And then this is the lowest. So let's have a look what's differing between the two of these. So between hexane and heptane, this one is simply just longer, right? Versus this one, which is shorter. Whereas the difference between pentan 1-ol is that it has an O and an H. When you're boiling things, you're putting heat into things to break bonds. You need to decide and say what those bonds are and why they're going to be, stronger/weaker, right? Now, the other thing as well is you're not breaking covalent bonds. If I have I2, that is the same as I covalently bonded to I. When you're breaking it, when you're boiling it from a solid, you're not breaking the covalent bond, otherwise you just have an I and an I, and that's not the same thing. What you're doing is you're breaking the bonds between these molecules, right? The intermolecular between molecule forces. So whenever you're boiling or melting, you're overcoming a force of some sort, and you need to explain that. So what I'm going to do is I'm going to start with the very obvious one, which is a pentan 1-ol, which is hugely higher to the rest. So you would say what you see first of all, and then the rest, right? So pentan 1-ol has the highest boiling point. Obviously, you write this in full. I'm just doing it shortcutted for the sake of time. If it's got the highest boiling point, we need to explain what that means. This implies that there's more energy needed to overcome, and because it's a molecule, it's intermolecular forces. You can't say intermolecular forces in something like a metal or ionic compound because they're not molecules. So it's more energy is needed to overcome its intermolecular forces, which are, in this case, ion forces, which in this case are hydrogen bonds due to the OH. That's not enough though, because we need to say why. These hydrogen bonds are stronger than the others, which only have London forces. Doing it that way will secure the bag. Now we need to figure out why heptane and hexane have different boiling points. So heptane has a higher boiling point than hexane, right? But the only thing that's different between the two of them is one is bigger. They both have, and you would say this, they both have London forces. So we need to think about why that's the case. The only difference between the two of them is that heptane's longer. So both have London forces, but heptane is a bigger molecule. That's the only difference between them. So that must mean this somehow explains why the London forces are stronger. There's nothing else in the question you can use to derive that. So what must be the case is that because it's a bigger molecule, it has stronger London forces. And then this should ring bells as to why. It will flag in your head, oh, this is why. It's because there's more. Well, there's two things. There's more surface for contact between molecules, and there's more electrons as well. There you go. So fuel additives are often used to improve the combustion of a fuel. N is a fuel additive that contains carbon, hydrogen, oxygen, and only, right? So the complete combustion of this mysterious N makes this much CO2 and this much H2O, and they've given you the relative molecular mass. Whenever you're doing anything to do with moles and this and that's, right, you cannot go into this without at least sketching out a vague expression of what's happening, an equation, right? So I know that it's going to be some mysterious N plus O2, which gives you CO2 plus H2O. Cool. Now, let's put the numbers in what we know. We know that this has an MR of 76, and complete combustion produces this much CO2. So we know that this mass that we've used of it is going to be 1.71 grams. Cool. Now, complete combustion of this produced this much CO2 and this much H2O. So we know that we made the mass of CO2 was 2.97 grams, and we know that we made a mass of water of 1.62 grams. Cool. That's all we know. It says calculate the molecular formula of N and then suggest a possible structure. So we can't just dive into doing lots of random bits and bobs, you know? We've got to kind of look at it systematically. All of the carbon in this CO2 will have come from N, because it's told you it only has carbon, hydrogen, and oxygen in it. So you can't just jump in and do the moles on this and that, blah, 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 because this has carbon, hydrogen, oxygen in it. So I should have really written that as well, C, H, and O. So our little thing that we're going to use to try and figure out where we're going back is by seeing how many CO2s we can get out of this. So what we're going to do is we're going to start by working out the moles of this CO2. If I work out the moles of CO2, it's going to be 2.97 divided by its MR of 44, which gives you 0.0675 moles. So we're onto something here. We know that there must have been in this original thing this many moles of carbon, because only carbon could have come from N. However, on the other side as well, H2O, oxygen will have come from both here and here, so it's not helpful, but the H's can only have come from N as well. So I can work out the moles of H2 as well and figure something out from that. So we'll get 1.62 divided by H2, which is over 18, which can be 0.09 moles, right? Now, this carbon and this hydrogen must have all come from the N. So I can work out the proportions of either of these, right? So what I mean by that is if I do a ratio of 0.0675 to 0.09, what I can do is I can work out the ratio of the C's to the H2s, right, using their moles, because then that can help me figure out how many we actually could get in an equation, if that makes sense, because this equation's made this many carbons and this many H2s. If I can get a nice pretty number between this, I don't know, 7 or whatever it is, then I'll know how many was in the original, which is why I'm doing this ratio. If I divide these both by the smallest number, I get 1 to 4 over 3. I'm going to keep it as a fraction because I can see these simplify by timesing both by 3. So then I'll get a 3 to 4 ratio of C to H2, right? So therefore, the original thing must have had 3 carbons and 4 H2s, not H's, 4 H2s. So therefore, it has 3 carbons and 8 H's. So then we at least know that this is going to be C3H8, right? But we still need to figure out where the rest of it is, this O whatever, because we don't know how many there are. We know the MR of this thing, so we can just figure out the MR of it and then take it away. So 76 minus 3 lots of 12 minus 8 leaves us behind with 32. So that means it's got to be 2, therefore it's got to have 2 oxygens. So it's going to be C3H8, H8O2. Done. And then it wants a structure of this. So let's just have a quick look. Is there anything else that's going on here that's useful? No, so it's just any way of really putting this in. So I'm just going to draw 3 carbons, 1, 2, 3. I'm going to put, so it's C3H8. So I'll put an OH here and an HO here. So to use up some of those hydrogens, right? So we've got all the O2s gone and we've got some of them. We've got 6 left. 1, 2, 3, 4, 5, 6. H. Done. So now it says Solketal has been investigated as a potential fuel additive. Solketal is synthesized from propane 1,2,3 triol and a carbonyl compound. Construct a balanced equation for this synthesis and then show structures for the organic compound. So you need to use what they've given you in the question to figure out what mysterious thing they've made is, because sometimes it isn't clear cut what they'll give you and what, that's the whole point. Your idea is to be able to derive what it could be. So the question's told you that it's from propane 1,2,3 triol. So let's draw that, right? So it's going to be OH here and an HO here, 1, 2, 3, and it's going to be triol here, right? Propane 1,2,3 triol, and they've told you it's with some mysterious carbonyl, and it eventually leads to this being made, where you've got an O here, you've got this, and then an O here, then this, here. You need to compare side by side what the missing in-betweeny bit is really, right? So if we have a look, we've got 1, 2, 3, 4, 5, 6. We've got 6 carbons in this, right? Whereas we only have 3. So whatever this mysterious thing is 3 carbons. And they've also told you it's a carbonyl. So your options are either it's an aldehyde or it's a ketone, right? Now we need to think about how these have interacted. So this has kind of gone off that way, off on its own business. This has kind of come back down here on its own. And then we've got 2 extra carbons sticking out. So whatever must have happened can't really be an aldehyde because it would just stick it on. If we did manage to try and stick it on, it would be stuck on in between in the middles. So it's got to be a ketone, and it's a 3-carbon ketone. So the only option we can make is just propanone like this. That's all it is. A scientist is researching compounds that might be suitable as fuel additives. One of these compounds give these analytic results. So we've got the elemental analysis by mass spectrum, and then H and MR spectrum as well. And the numbers are the relative peak areas. When the spectrum is run without D2, there's 2 additional peaks with these and there. So then it's probably asking us to deduce the structure of it and show your reasoning, right? Now, when you're doing this, do not jump back and forth all over the place trying to work bits and bobs out. Do it systematically, step by step. Otherwise, you'll get confused with your working and you'll lose out and just completely get lost. So what I mean by that is let me just get the data sheet. So what we're going to do is we're going to work through this step by step, okay? So what I mean by that is get all of the information first, then put the pieces together. We know it's elemental analysis by mass, so immediately we should start by doing the basics, working out its empirical formula. So if we work out its empirical formula, what you're going to do is you're going to do its ratio of C to H to O. So we know it's 54.54% divided by 12, 9.10 divided by 1, and 36.36 divided by 16. If you do that, you get 4.545 to 9.10 to 2.273. If you divide it by the smallest number, which is here, you get a ratio of roughly 2 to 4 to 1. Therefore, the empirical formula is going to be C2H4O. Now, they've told us what the mass spectrum molecular ion peak is here, which is this, right? So if we work out the MR of this thing, it's going to be 2 lots of 12 plus 4 H's and then 1 oxygen, which is going to be 44, right? If I do 132 divided by 44, I end up getting 3, right? So 132 divided by 44 equals 3. So that means its molecular formula is 3 times this thing. So we now know the molecular formula is going to be 3 times that whole thing. So it's going to be C6H12O3. That's one piece of information done and dusted that we can really make use of. Next, it says here's the proton NMR spectrum in D2O, and we've got 1, 2, 3 clusters of peaks. However, the question's told you there are 2 additional peaks when you're running it without D2O. The reason is because that D2O is eliminating OHs. So here, without even diving into the other stuff yet, always write down the basics. I know immediately, first of all, that this NMR spectrum has 5, 3, but then there's other 2, so 5 peaks. Therefore, there are 5 hydrogen environments. A lot of people miss this part out, which is I find really bit odd. This is really helpful for figuring out what it's going to be built like in the end. Next, what we do is we go step by step through each and every single peak, one by one, and figure out what they are. So I'm going to start with this one here. You would write the peak at 1.3 ppm. And don't dive into trying to figure out what it is from the table. Characterize it first. What I mean is get everything. So it's a peak at 1.3 ppm. So we know that this is a doublet, which means the adjacent carbon has 1 hydrogen. And we know it's got an area of 3. So this means that this has got to have 3 H's on it, right? You do this first before diving into what it is. Because then when you pick it out, you know what you can put onto it straight away. And you can figure out like a chunk of the molecule. So here I can see that this is this peak here. And it's this hydrogen in bold. They're in bold because that's what was picked up by the machine. Now, if that's in bold, and there's an area of 3 of those bold hydrogens are picked up, as in this is going to be here like that. And it's told you 3 H's, but the adjacent carbon has 1 hydrogen. So the adjacent to this one, as in what this R group would be, it's not always what the R group is, be careful, but it's going to be, adjacent to this, which means it's going to have 1 hydrogen next to it. So you've got something with 1 hydrogen and then something else on it and something else on it that's not hydrogens. Fine. Let's look at the next one. So the next one is this big one here. So that's going to be what, actually, that's more of a 1.2 to be honest. Here we will have one at like 1.4 ppm. Again, same thing. We can see it's a singlet, so the adjacent carbon has no hydrogens, and we know its area is 6. So it's probably going to be 6 H's. It's most likely going to be 2 lots of CH3, because how else are you going to stick 6 H's around something, right? It's within this range again, and it's this hydrogen environment picked up. So there's one singular peak with 6 of them. Those 2 CH3s have to be in the same environment. So what we'll have is a carbon with CH3. These would be the bold ones that picked up. Another CH3 in the exact same environment, right? And then the adjacent carbon has no hydrogens. So then there's some other mysterious thing bonded here, because this can't have anything else on it, or hydrogens-wise, for now, based on this data. And the adjacent carbon has no hydrogens. So there's something else bonded to it with no hydrogens. That's chill. Fine. Then our next peak is at this 4, right? So you would write the peak at this 4, same thing. We know that's going to be, if I zoomed in, it's a quartet. So the adjacent carbon has 3 hydrogens. We know it's got an area of 1, so therefore it's got 1 hydrogen on it, right? So then we need to figure out what piece that is. If we look at the data sheet, if we look at where 4 is, it's HCO, HCl, HCBr. Now this has only got carbon, hydrogen, and oxygen in it, so it can't be either of these two. So it's got to be this HCO. So the HCO has got 1 hydrogen, the one in bold, right? C, it's bonded to an O. The adjacent carbon has 3 hydrogens. It's not here because it's not adjacent to this one. It has to be adjacent to this one in bold. So what happens is we have a CH3 like that. That's why this is this piece here. So we've got that, we've got this left behind. Now, the question's still not done because we've got 2 other peaks with these peak areas here and here. right? If we're running it without D2O, these both are going to be OHs, right? So we've got an 11 ppm and a 3.6 ppm, right? And these are going to be OH and OH. Now, the thing is here, these are different peaks, so they're different OHs, right? If you look at the overall formula, it's O3, so I only have these left. I can only have OHs. There's got to be something else with an O in it, so it's probably going to be that I have a carboxylic acid in here as well, because there's no other way I can get around this, right? One of them's at 11. You can see that this is a carboxylic acid COOH, right? So now we definitely know that there is a COOH in this. Cool. And we know there's another just standard OH here as well. So now get all the pieces of the puzzle together and then put them together. So what we know in this thing in total is that it has 5 hydrogen environments. It's got this as its overall formula. It has a COOH and an alcohol in it and these pieces. So we need to piece these together to try and fit the bill. So grab these pieces one by one and just add them together until you get what you want. So what I'm going to start doing is taking, like, for example, U, because that's the most exciting, and I can see there's probably going to be an OH on here, right? So I'm going to do H, C, CH3. I know that this carbon has to have something else that isn't a hydrogen, and I know this is an O, and we have an OH, so we've got an OH there. So I've dealt with one of these OHs. Cool. Now the next piece could be something else. Let's have a look what we have. We have a carbon with 2 CH3s bonded to a carbon with nothing else on it, or it could be a carbon with a hydrogen and CH3s, right? Now here, so now we have a carbon with a hydrogen that needs to be bonded to other bits. Now can you see here we have this here, which is a CH3 with a carbon and a hydrogen, or it could be 2 CH3s and a carbon with nothing on it, right? So what I'm going to do is I'm going to put this with a carbon with nothing on it because that will make me get lots more out of it, if that makes sense. So here, it'll be a carbon with 2 CH3s, for example. So it would be CH3, H3C, and this is bonded to another carbon, right? So if we've dealt with you now, what's left is we have this piece here, right? But if you see, that's a CH3 with a CH next to it. Is that not the CH3 with a CH next to it there? So that's that piece actually there. All that we're left with is we're left with a C double bond OH because we haven't dealt with the carboxylic acid. So it's this C double bond O, HO. So now we check the formula. So 1, 2, 3, 4, 5, 6. It's got 6 carbons. 1, 2, 3, 6, 9, 12. It's got 12 hydrogens. It's got 3 O's. And then we need to check, has it got the right number of hydrogen environments? So here, that's 1 hydrogen environment. This one's different. So there's 1, there's 2. Now this is going to be 3. This and this are the same environments of 4 and 4, and then 5. That's how you do it. If you do it like that, that'll help most, and you'll get the most sort of luck with it. Now this is tricky. So if you follow in those steps, at least if you show your reasoning and what each piece means, you can get about 4-ish marks out of 6 easily like that. So just make sure you do it that way. Don't jump back and forth. Anyway, I hope that helped. Please like, share, and subscribe. You know the drill.